Part B of our questions reads as follows. So we are having the first question is number 6. A farmer wants to build a rectangular pen using 200 meters of fencing. One side of the pen will be along a river and does not need fencing. What dimensions will maximize the area of the pen? Number 6 is kind of the same as number 3. It's just the same thing. Try and solve number 6 and see what you are getting, and then if you are not getting the same answer as me, then you can check how I did it. And also, what is also important here is that if you are confident with your answer, just check my answer and then you can move on to other questions. Like I always say, you don't have to repeat something that you already know. Just look at other questions that you don't have a clue how you can actually solve them. So that's what you can actually do. Let's see how we can actually solve number 6. So the first thing that I want you to realize here, we are at number 6, and number 6 is saying that we wanted to create a rectangular pen. So this side, there must be a side, there must be this side, and of course there must be this side. But the question is saying that this side is along the river. So we are having a river this side. So we have a river because this is a rectangle. If this is x, this must also be x, and this side must be a y. It can either be equal to x or not. Of course, if it is equal to x, we don't have a rectangle, we have a square. But for us now, let's assume that from this point to that point, from this point to that point is equal, but we're only gonna fence these 3 sides. And now we already have a fence, and this fence is about 200 meters. So if I start here placing my fence and go all the way and end up here, the length of this fencing must be 200. In other words, if I'm adding x plus y plus that x, I should end up with 200, or the perimeter of these 3 sides must be a 200. In other words, you are having a 2x plus a y must be equal to a 200, or we can say we have y is equal to 200 minus a 2x. The next thing here is saying, the question is saying, what dimensions will maximize the area? So if we wanted to maximize the area, the first thing we need to know, what is the area of this rectangle? The area is always going to be this side times that side to get the whole area of this rectangle. So A for area, we're going to say this area is going to be equal to x times a y. And of course, we know our y, that we can actually say that our area is equal to x times 200 minus 2x, which is just the same as 200x minus 2x squared. And then of course now you can see that once I substitute the y, this is actually going to be a function of x, area as a function of x. And if you are having an area function, which means you must have a domain, what can actually happen with x? Again, our x cannot be 0. We know that 0 must be less than x. And let's look if we have the output, the upper bound here. So if x cannot be, if x was equal to 0, then we're going to have just a straight line. This is not a rectangle, it's just a straight line if x is equal to 0, because this is going to be 0, and then we'll end up having only y, and y is going to be the whole fence, so we cannot have that. And if, let's say, we're having our y equal to 0 here, we will end up having a river this side and a fence only that side. So if we're having this one equal to 0, but because we are having these 2 sides, which means we will end up having our 2x plus y equal to 0, but our y, if y is equal to 0, then we'll end up having, this is 200. we'll end up having our 2x equal to a 200, and then we'll end up having our x equal to a 200 divided by 2, or x equal to a 100. So if you look into this thing is actually saying that once you make this equal to 0, we'll have a fence going up and then it comes down. We have an x this side and an x this side. These two needs to be equal because the fence needs to be 200, so this must be 100, and also this side must also be 100. In other words, our x can never be above 100. That's one way to look into it. Can it be equal to 100? If it is equal to 100, we are having a straight line going up, so that is actually not a rectangle, that's a straight line. That is why we don't have equality. So that is the domain or the restriction of this area function that we are having. The next thing is just find the first derivative with respect to the x here, and then of course the first derivative of this is going to be 200 minus 4x. And then after you have done that, the next thing that you will do, you need to set this equal to 0. In other words, 200 minus 4x must be equal to 0, or 200 must be equal to a 4x, and then divide by 4 on both sides, and then 200 divided by 4, that is a 50, is equal to this, divide that, and then we have an x there. So we are having our x here. Now that we are having our x here, this is one of the values that make this equal to a 0. Of course, we don't have to check if the values of x that are actually making this undefined, because this function is defined everywhere. It's a polynomial, so we only end up here. So the next thing that you end up doing here, you want to find the area when x is equal to 50. You get that. The second thing here, let me use a red here. I'll explain in a moment why I'm using a red. The area when x is equal to 0, and then you also want to find out what is the area when x is equal to 100. So now that you are having this, you will find out that here you actually end up having you take this 50, you plug it in the original area. It's going to be 200, and then you have a 50 minus 2, and then you have a 50, and then you square it up, and then you can see here that we're actually having the almost the same thing here, that this one is going to be, let me just use this, we have 200 times 50, and then minus 200 times a 50, but now we are squaring it up. The answer we're getting is a 5,000. Because we're having meters, so it's going to be meter squared. That's the area. If we are plugging in a 0 here, we'll end up having a 0 area. If we are actually plugging, because we'll end up having 200 times 0 minus 2 times 0 squared, which is just a 0 meter squared. And then here we are also end up having 200, and then we have 100 minus 2, and then we have 100 squared here. What are we going to get? We have 200 times 100, and of course if you look into this one here, 100 squared is the same as 100 times 100, and of course 100 times 100, you know, that's just a 100 times 2, that's just a 200. So we have 200 times 100, 200 times 100, so this is also a 0 meter squared. The reason I'm writing this as red is because we don't have equality here, which means you really don't have to do this in this particular case, but I'm doing this so that you get to understand the steps that you have to check this, you have to check that, you have to check that, and then you look at the one that is largest, because we want to maximize the area here. So this one is the largest of them all, which means that the absolute maximum area is equal to 5,000 meters squared, and with dimensions. So we are having our x is the value here that is giving us the largest value. So we are having a 50, meters, and our y is going to be, what is our y? Y is equal to 200 minus 2x. So here is supposed to be 200 minus 2x, but our x, we know now that it is a 50. And of course, if you look at 2 times, if that's 100, so 200 minus 100 is 100 meters. So that's how you actually solve this particular problem. Let's look at problem number 7 and see what we are actually getting. Number 7 is saying a rectangular box. So we wanted to create a box with a square base. Let me make this big. A rectangular box with a base, with a square base and an open top, must have a volume of 32,000 centimeter cube. Find the dimensions that minimize the surface area. Also, another thing that I want you to realize, when we're having a centimeter cube, you must also know that within this box we can contain 32,000 milliliter. So centimeter cube is the same as milliliter. So you can see that when you're drinking that juice, you can actually know how much do you need to actually store or contain a certain juice of a certain amount. So that's what is important here. And also another thing here is we need to understand what do we mean by rectangular box with a square base, and the volume is given, of course. So we are at number 7 here. We want to build a rectangular box, and you can see here they are telling us that this rectangular box must be of, hey, this is bad. This is really bad. Let me try and create something that looks a little bit cleaner or nicer. So a box should look like this, and of course look like this, and have something of this type here, and then we have that. I'm trying to be a little bit creative here. We're having that, and of course we are having this one here, and then this one goes there, and then we are having that, and of course that side we must also have something of this type here, and then this one needs to go there. At least my box is not that bad, but what is important here is this. This question is saying open top. So the top here, if you look at this top, is open, but the bottom here, this bottom is actually not open. What am I doing now? So it's not open. In other words, I cannot really see this because it's somewhere on the other side. It's just somewhere on the other side. So from this point, I don't see that it is from the other side, and of course I don't see this line there because it's on the other side. The next thing that I want us to realize, because it's open, that's why I can see that. So they are saying this is actually a square, which means if this one is x, this one must be x, and this side must be x, and that side might be x. The same thing here, we have this is x, that side is x, that side is x, and that side is x, because it is having a base of a square. And then this side here, I'm just going to call y, which is the height. So this is going to be y, and all of these are going to be y, and we're having a y there. The next thing that we also need to know here, the volume of this box here is going to be the height times the base times the breadth. So we have LB H. So what is the length is going to be x times the base, which is also x, and then y. So we have x squared y. That is our volume here. Let me write it cleaner. So we have x squared y. That is the volume. And the next thing they are telling us here is that the volume is 32,000. In other words, x squared times y is equal to 32,000. So if I divide by x squared on both sides, I divide by x squared, I'll end up having my y is equal to 32,000 divided by an x squared there. That is what is important here. And then we are having this y here, which is actually given. So we wanted to actually maximize, or maximizing or minimize, find the dimensions that will minimize the total minimize the total surface area. So we wanted to minimize. First, how do we find the total surface area of a box like this? So we will have the area of the bottom. The area of the bottom, if you look at the area of the bottom, it is the area of the square, which means we have x times x, or just an x squared. And then we look at the area of the side. So if you look at the area of the side, so we are having all these sides. How many sides do we have out other than the bottom? We have this side here, which is on the left. So we have that side, and then we're also having this side here. So we have that side and this side, and then we have the front side, and then we have that side there at the back. So the height of this side is y, and the length or the breadth of the side is just an x. And you can see that all these sides, all these four sides, are actually having the same height, which is y, and they're also having the same length, which is just an x. So each of these sides will have an area of y times an x. So that will be the area, and we are having 4 of these sides. So we are having 4 sides that are having the same area. But the top here, they are telling us is open, so we don't include it, which means now the total surface area is going to be the area of the bottom plus the area of the sides, which is just the same as x squared plus 4xy. Let me write it to be cleaner. X is equal to x squared plus 4xy. But now, if I replace my y by this equation here, I will have this surface area as a function of x, which means we'll have x squared plus 4x. Instead of y, I have 32,000, and then I am dividing that by x squared. And you can see that something magical is happening, because when you're having a 32,000 and then you are multiplying it by a 4, you will notice that you are having 128,000. So this function here is the same as f of x is equal to x squared, and then you have plus, and they have 128,000, and this x will cancel with one of those x's, and you'll be left with one x at the bottom. So we're having this surface area function, but when you are having a function, it must have a domain. So the domain of the surface area is supposed to be something like this. So you can see that the only thing that we have here, we are only knowing that our x here cannot be 0, because once x is equal to 0, we will just end up with a straight line going all the way up. And when x is equal to 0, we're not gonna end up with this volume that was given to us as 32,000. So x cannot be less than 0. So we have 0 must be less than x. Right, so and also x cannot be negative, because this is the length of a function. And then the next thing here, we cannot have a y equal to 0, because if we are having a y equal to 0, we will not end up having that volume there. So y cannot be a 0. That's also something that we know that cannot happen. Y cannot be 0, must be less than a y. So these are also some of the things that we want. And also take a note here, if we have x equal to 0, this will be undefined. That is y. And now, what is the maximum value that we can our x can actually be? We don't really know what is that, because it's not contained in the statement, and it's not clear from us that we can get our our x here. So our domain is just gonna be, our restrictions will just be of this type, and our domain will just gonna contain it like this. Once we have that, the next step is to find what is the first derivative with respect to x. First derivative of that's going to be 2x plus, and of course if you look into this, is the same as 128,000 times x raised to minus 1 when you're having it in a denominator. So when we are taking the derivative of this, we're just gonna bring this up front, so we'll have a minus 128,000 times x, and then we subtract a 1, we'll have a minus 2. Of course, when you're having a minus 2, you are also having an x squared in the denominator. And if you notice here, you can see that this thing here is the same as 2x times 1, and then minus 128,000, and then divide by x squared. And then when you're having a 1 here, 1 is the same as x squared over x squared. This x squared that I'm taking here is this, because I want to end up having a lowest common factor, lowest common denominator. That's my mistake. So we have this common, actually is the highest common denominator. So we'll have this x squared because we're having a denominator x squared, we have an x squared here, so it's the highest. And then the next thing is we take this as it is, because we have a 1 there. X times x squared is going to be an x cube. We have the 2 as it is, minus 128,000. And then the next thing that you want to do, you want to set this equal to a 0. So the first thing that you want x prime of x to be equal to a 0, and then solve for x. So once we are having that, you will know that this is only going to happen if the numerator is equal to 0. So when you are having 2x cubed minus 128,000 equal to 0, that's when this is going to be equal to a 0. Other than that, it will not be equal to a 0, because if you are having the denominator equal to 0, you will get an undefined. So the only case is when the numerator equal to 0. Then we solve for x. Because this one is on the left is negative, this side is going to be on the right. And then you divide by 2 on both sides. You divide by 2 on both sides. This 2 and that 2 will cancel out, and then we have x to the power 3. And then this side you will have 128,000, and then you divide that by 2. Of course, we'll end up having a 64,000. You can always get this even if you are not sure. You're just gonna ask yourself how many 2's are contained in 12. There are 6 of them, there is no remainder. And then how many 2's are contained in 80,000. You will find out that actually you have 4,000 of those. Or you can ask yourself how many 2's are contained in 8. There are 4 of them. How many 2's are contained here? 0, 0 and 0, and they don't leave any remainder. So you're having that thing here, and then your x now is going to be the cube root of 64,000. And then of course I'm going to just raise that to 1 over a 3. So the answer we're looking for here, our x is equal to a 40. The next thing that you are looking for here is this. You wanted to find x prime of x, and you wanted to find it when this one is undefined, because we are looking for the critical numbers here. So we look for when it is equal to 0 and when it is not. This one here is undefined when denominator equal to 0. In other words, this is going to only happen if you are having x squared, because this is the denominator. When we are having an x squared equal to a 0, which simply means when x is equal to a 0. But x is equal to 0 is not part of the domain. Not part of the domain of s of x. So but this one is not part, so we don't even have to check that because it is not part of our restrictions. So that is why this one I was writing it reddish, because it's not part of this. But once you have done that, the next thing that you have to check, you need to find out what is s of 40, because the first x is 40, and then the next thing that you want to find out, what is going to be s of 0. This 0 here is actually the same as this 0. No, it's not really this 0, but okay, we can say that it is the same as this 0. But what I was referring to this 0, which was part of the intervals that were given for this function, because we cannot have a 0. But because we are having we don't have equality here, so we don't have equality. So since we don't have equality, we don't have to check 0, but it is the steps we have to end up checking this one here. But we're not supposed to check it because it's not part of the domain. If it was part of the domain, we're supposed to check this. And of course, if we had some values here, we also had to check them. This one, we know that that's just an undefined. And also this one now is the one that we're supposed to check, because what you need to do here, you need to end up going back to the function, which is a squared plus 128 divided by 0. So we are having a 40 and then you want to square it up, and then you had a plus, and then we have 128, but having several thousand there, and then I'm dividing this by a 40, and then this one here is 4,800. So this one is supposed to be 4,800. So this is the only value because we don't have anything there. So the next step, you can just say that therefore the absolute, because we're looking for the minimum, so the absolute minimum surface area is this 4,800. It's 4,800, right? With dimensions. So my x, we know that it is equal to 40, and what will be our y? Our y, we had our y here. What was our y? Our y is equal to 32,000 divided by x squared. 32,000 divided by x squared. So our y was 32,000 divided by x squared. But our x, we know that it is 40. So we have 40 squared. And then of course it is equal to that. So we have 32,000 divided by a 40, and then we square it up. So we end up having a 20. So these are the dimensions we were actually looking for. Let's go to number 8. What is going to be our number 8 here? We are checking for number 8 and want to make sure that we are actually getting some understanding here. A poster have a total area of this here. Let me check here something that I missed. We were given centimeter cube, so this one's supposed to be centimeter and this one is supposed to be in centimeters. So those units are also important. So let's go to number 8. A poster must have a total area of 600 centimeters squared with 4 centimeters. Okay. A poster must have a total area of 600 centimeter squared with 4 centimeter margins on the top and bottom and 2 centimeter margins on the sides. What dimensions of the printed area will maximize the visible printed region? So one thing that I want you to realize here, when they're saying a poster, this question is assuming that your poster is going to be on an A4 paper. Number 8. Let me write number 8 here. You have number 8 here. So number 8 is saying you are about to create a poster. My poster is too bad. So we are having a poster here, and our poster is going to be of this type. So we're going to have a poster of this kind. And then another thing that you have to realize here is that this poster here is actually going to have this length here. I'm gonna call this length X. This is not good looking. This is going to be X. This side, of course, that side will be X, and this side is going to be Y, and this is going to be Y. We are not creating a poster that has some circular region here. We are only talking about a rectangular poster. That is what this question is assumed to be. And of course, you can write that one down if you are not sure if is this poster going to have a circular paper, or is going to have, we are just using a normal paper here, which is a rectangle or an A4 or an A3 or something, but it must be in a rectangular shape. And then the next statement here is saying that this poster here, this is the whole poster, must have a total area. So if I am taking X, remember that the area is equal to this side times that side is going to be XY. It must be equal to, they are saying it's supposed to be 600. In other words, XY is equal to 600, which simply means our Y is equal to 600 divided by an X. So we have our Y in terms of X. In other words, we have eliminated a Y. That is what this question is saying. The total area is equal to that. A 4 centimeter margin on the top and bottom, and 2 centimeter margin on the sides. So moving from this up to here, let's say I'm moving like this. Let me write this. So this question is saying there must be a space here. This must be just white, and also here there must be a space. And moving from here up to this position, this and also here, we must actually end up creating this space here, and this space must be they are saying that on margins we have 4 centimeters top. So this one must be 4 centimeter, and this one here must be 4 centimeter, which means there is an empty space here, and there's also an empty space there. That is what the question is saying. And then it says on the sides there must be 2 centimeter margins on the sides. So also on the side here, on this side here, I mean there are 2 sides here, and also this side here, we must have this one from moving from this point to that point, and moving from this point to that point. So we'll have 2 centimeter, and also here you have 2 centimeter. So we have 2 centimeters on each of these sides. So this region here is the region that will actually be printed. So what I want you to realize here is that you can see that from here we have also that. So if this one, remember that this one is 2 centimeter, and this one is also 2 centimeter from here to there, which means this length here must be actually 4 centimeter. From here up to here we have X, so this is going to be X minus this space that is empty, and also minus that one. So it's going to be X minus 4 centimeters. So we are having X minus 4 centimeters, and also the height from here to here is 4 centimeters, and from here to here is 4 centimeters. So this height of the printed region here is actually going to be Y minus, we have 4 and 4, so it's supposed to be Y minus 8, and of course this side also is going to be Y minus an 8. So that is the information that we are getting from the statement. Find the dimensions that what dimensions of the printed area will maximize the printed region? So the printed region is going to be that. So we wanted to find the area of the printed region. So the area of the printed region is going to be the one side times another side of course, one side we know that this printed region, one side is x minus 4, so one side is going to be x minus 4 and the other side is going to be y minus 8. So that is what is actually happening here. The next thing is to simplify as much as possible, but I want to have my a as a function of x before I can simplify anything, because I don't want to end up dealing with so many things. So I'll end up having x minus 4, and then instead of y, I know y is the same as 600 divided by x minus 8. And of course here I can say that I'm having an x minus 4. And then on this side here, I have a 600 over x minus 8 x over x. So what I'm doing here, I took this x, I multiplied the numerator and the denominator because this is the same as 8 over 1. So I multiply and divide this because x and x will cancel out, and then we'll end up having the same thing there. But I'm doing this so that I can have a common denominator. So I'll end up having x minus 4, and then I will have 600 minus 8x all over x squared. No, not x squared, because I want the common denominator. So I will have take one of these x's. Then once we do that, I multiply this by 600, so I will have 600x. I multiply this by that, I will have minus 8x squared. And then I multiply this by that, 600 times 4, I have 600 times a 4. And you know that we're supposed to have 2400, so we'll end up having a minus 2400, this one and that one. And then I multiply this one and that one, will end up having a positive. We have a 4, and then you multiply that by an 8, you will get a 32. You have a 32x. This whole thing will be divided by x because there is just a 1 here, so I'm multiplying that with that, so it's a 1. Just to double check, this and that is positive, this one and that's supposed to be negative, but we have an extra x. This one and that's supposed to be negative, there is no x, so we have 2400. This one and that's supposed to be positive, and we're supposed to end up having a 32 and 1x. And then we simplify this one and that one, 32 because positive, and then plus 600, so I will have 632x. That's what we are having. And then I have minus 8x squared minus 2400 all over 1x. So that is the first thing that we are actually getting here. So we are having, let me do this. So we are having the area as a function of x is the same as 632 minus 8x minus, is it minus or minus? This was minus, those two were positive. Okay. And then we'll actually end up minus 2400 all over an x. Can you see that I divided by x here, I divided by x here, and then I divided by x? Why am I doing that? So that I can take my derivative easily. And of course, you know that this thing here is the same as 2400 times x raised to minus a 1. Having a minus, it means it is in the denominator. The next thing, you take the derivative with respect to x. This one is a constant, so it goes away, so we'll end up having minus 8 for this one. And then for this one, because we bring the 1 down and it finds a negative, so we'll end up having a positive 2400 times x raised to minus 2, because when I'm minusing a 1, they will get a minus 2. And when I'm having a minus 2, it means that this one is actually in the denominator. So that's the first derivative. Did we actually find out what was the domain of this? The only thing that we know here is that to find the domain, because the domain is always needed, we know that our x cannot be equal to 0. So we don't want this whole side to be equal to 0. So if our x cannot be equal to 0, we know that at this point we can say that the domain, just for the domain purposes, I have 0 must be less than x, And let's look at x again. If you look at x, because when I'm multiplying these two, there is nothing that can be said. I also know that y cannot be equal to 0. So I'm only also having 0 is less than a y. That's what we actually know. We don't know much about the max at the maximum value x can have. Then the next step that we are having here, we want to check what are the values of x that will make the area equal to a 0, which means I want minus 8 plus 2400 divided by x squared to be equal to 0. One thing that I want you to realize here is that this thing here is the same as this, same as minus 8 times x squared over x squared. This and that will cancel out, plus a 2400 divided by x squared, which is the same as minus 8x squared plus 2400 all over x squared. That's what I wanted you to also see, so that this one can be written properly as minus 8x squared plus 2400 all over x squared. When is this going to be 0? It's only going to be 0 when the numerator is equal to 0, plus 2400 equal to 0. So that's only the case when this is going to be equal to a 0. The next thing that we need to do, take this to the other side. So we'll end up having minus 8x squared is equal to 2400. Because it was positive, it has to be negative that side. And then I divide by minus 8 on both sides. And then I will end up having x squared must be equal to, when you are having 24 and then you have 2400 and you're dividing it by 8, you will find out that you are having a 300, because the negative and negative will cancel out, and you know that there are 3 4s, there are 3 8 in 24, 8 16 24, we have a 3, there is no remainder. How many 8 are in 0? We don't have any, no remainder, and also here 0 0. And then after that, our x is supposed to be equal to plus or minus the square root of 300. But now, because x is the length, it cannot be negative, so we only focus on the positive one. And then you can just raise this to 1 over a2. So this one, our x is approximately equal to 17.32 centimeters. And then what will be our y? If x is equal to that, we don't know yet, but we have a function to do that. The next thing that you're supposed to do now, you want to find values of x such that the derivative is undefined. So if you are looking for this value to be undefined here, is when the denominator is equal to 0. Remember that this is equal to this, so you can see that your denominator must be equal to 0. And the next thing here, if you look at our denominator is just, what is happening here? This was supposed to be x squared, but it's not changing anything. It's supposed to be x squared. All the calculations are still the same, which means that our x squared must be equal to 0, which implies that x must be equal to 0. So if you look at this x, but x is equal to 0 is not part of the domain. So it's not part of the domain of the area. So basically, this one here, we're not even going to check it because it was not part of the domain that we had here. And also, even if you did not have that, when you are plugging it in, you will end up getting undefined. When you are checking it up, it's still fine, even if you don't have that. When you're checking it up, it will tell you that that cannot happen. The next step that you want to find out, what is the area when x is equal to this value here, which is the square root of 300. what will be the area. The next thing that you were supposed to also check is the endpoints of the domain, but in this case we don't have any of that because we don't have equality here, so you don't have to check it. We only want to find out what is the area of this and what was our initial area. So if you look at our formula here, our area formula was this thing here. We have this, so we're going to end up having 362, and then inside you will end up plugging in at the square root of 300, and then after that you say minus 8, and then inside you have the square root 300, and then from there you can square it up, and then you can say I want to subtract 20, you can subtract 2400, and then at the end of the day you divide by the same thing, which is square root 300, square root 300. So the final answer that we are actually getting here is 354. So here your area is supposed to be 354, right? And then because there is nothing to compare with, you can say that the absolute, the question we're trying to find here is the want to maximize the area, the absolute maximum area is 354 centimeter squared. We want to have 364 centimeter squared with dimensions. So what dimensions of the printed area? With the dimensions, so our x here is equal to the square root 300. It was equal to the square root 300, which is approximately equal to 17. What's this? Which is equal to 17.32. So we have a 32 centimeters here, and then our y here is going to be the same as what was y. Where is y? Y is the same as 600 over x. So our y is 600 over x, so we're having 600 over square root 300. And of course you can say that I have 600 and then divide by square root 300. What is the answer? The answer is approximately 34.64. That is the value of x, that is the value of y. These are the dimensions of the paper. The actual dimensions should be of the printed region. So if this poster here margins side, what dimension of the printed area? So here we are looking for this one here. So our y, we need to subtract an 8 to get the actual dimension. Our x, we need to subtract a 4. So the actual dimensions that we're looking for, the actual dimensions of the part that have some images, if we remove all the other parts, so we'll end up having, I'm gonna call this an x prime, so it's going to be 17 minus 4. Let me first subtract an 8 here. So we'll end up having, and our y prime is going to be 26, is approximately 26.64, and then our x here, I want to subtract a 4, so it's supposed to be 13.32 centimeters. So this one is the part that will not be empty, and this one is just the dimensions of the paper. This one are dimensions of the printed region. So that's how you actually end up solving problem number 8, which was saying something very nice, that look at the part that is actually printed, and then you will see that all these answers are actually going as we wanted them to be. So we have that. Now we wanted to deal with number 9 and number 10. Number 9 is saying A cone is to be made from a wait, number 9, right? Let me go a little bit down, focus here, let me write here. So we're having a number 9 here. Number 9, let me put it back. A cone is to be made from a circular piece of metal with a radius 10 centimeters by cutting out a sector and folding it into a cone. What is the radius of the cone that maximizes its volume? This problem might seem a little bit difficult, but it's not that difficult because we wanted to create a cone out of a circular metal. So basically here we are actually having a metal that is this it's a circular metal, and it has a center, and from the center to the outside we have a radius, and the radius in this particular problem here, let me check this problem, the radius is actually 10 centimeters, so it is given as 10 centimeters. So this radius here is actually 10 centimeters. And now we want to cut this one here and then create a cone. A cone is actually having a shape of this kind here. So that is how a cone usually looks like. Let me try and make sure that I draw it nicely. I'm gonna take this and then want to create a cone of this type here. And then this is the cone that we are actually going to create. The question you might be having here from this cone is how can we actually create a cone out of this circle here? This is how this thing is actually done. I can't really draw it and show you how this thing is done, but I want you to see this, that you are having this nice thing here. So you're having a circle of this kind, and then you fold it, and then you end up getting something like this. So that's what you end up creating. Let's look into it. That's what you are getting here. You end up cutting, and then after cutting you fold it like that. That's how we end up creating this cone here. So this is what we will end up getting. I also want to show you something here while we are creating this. So when you are having this circle here, you cut here. This is the radius. So once you cut here, you will find out that once you fold this side here, let me pause somewhere here. Once we cut, and then after cutting, you can see that that side that was a radius, it becomes the slant height or the slant side of the cone. So the radius is just the side of this cone. So basically from this circle, once we cut it here, we will end up having this R on the side, which is 10 centimeters. And then the radius of this cone, we don't know it. And also we're having a height here. We have some height, and this height here is just h. And let's just for good reasons write this as capital letter R, the radius of the circle. In other words, the slant side of this is going to be R, so that the radius of the cone is going to be R, right? Small letter R. And then let's go back to the question. A cone is to be made. What is the radius of the cone that maximizes its volume? So the first thing that we need to find out here is that what is the formula for the volume and the total surface area of a cone. The first thing that you need to realize here is that the volume of a cone is supposed to be 1/3 pi r squared h. That is the volume of a cone. So we are having this volume here. Yeah, so we have this volume here, and also the surface area of the cone. This one is for the cone, and then the surface area of the cone, just in case you don't know, because the surface area have this circle here that is at the bottom, so it must have a pi r squared, which is the surface area of the bottom here, or the sitting side. And also then the body of it is going to end up having pi r. I can use this r here. This r here is the capital letter or slant r. Other people usually use L to say the slant r, the slant height. It's just that it's this side here. That is the total surface area. The question is saying that what is the radius of the cone that maximizes its volume? We want to maximize its volume. So basically, if you look into this here, the only thing, so we have a volume is 1 over 3 pi r squared h. So the only thing that we are actually not having here is the height. So we want to write the height in terms of the radius. So if you look here, this one, because this is a perpendicular height, so it is perpendicular. So if you are looking at this triangle here, you will find out that using Pythagoras theorem, because this side is a hypotenuse, because this is opposite the 90 degrees, so it is a hypotenuse. So if you are having r squared, it must be equal to h squared and then plus r squared. In other words, h squared must be equal to r squared minus small r squared, or simply put, our h is supposed to be equal to plus or minus the square root of r squared minus small letter r, but h is the height, so the height is always positive, so we are only having the positive. So the volume as a function of the small radius of this cone is going to be 1 over 3 times pi r squared, and then when it comes to h, we are having the square root of r squared minus r squared here, capital letter and the small letter. And then of course you know that this is 1 over 3 r squared, and then inside here I'm having the square root of 10 minus r squared. That is what is important here, but we have a square there, so we square it up, or you can say that 10 squared, it is just 100. So that's how you end up solving this problem here. We are having this and we want to maximize its volume, so we don't have dimensions much here. We know that this one cannot, this side cannot be 0, and this one cannot be 0, and this one cannot be 0. That's the only thing that we have as the restrictions. We can just say our r is greater than 0. That's what we know, because once the radius is 0, then we don't have a cone anymore. Then the next step is you want to find the first derivative with respect to r. You can see that we are having, we're supposed to end up having 1 over 3 by this is just a constant, and we wanted to actually find the derivative of this. So the derivative of this is a multiplication of two functions, which means we end up having 1 over 3 pi r squared times 100 minus r squared, all raised to 1 over 2. So the derivative of this part here, because this is just a constant, is going to be 2r. We're using the product rule here just for you to know. So we're having 2r, and then we keep 100 minus r squared, and then we have this 1 over 2, and then we say plus, and then we keep r squared, and then we take the derivative of this part here. So we'll end up having 1 over 2, and then we'll have 100 minus r squared, and then we have a minus 1 over 2, the derivative of that, times the derivative of what is inside. So it's going to be minus 2r. So I want you to just take you into taking the derivative again. We take the derivative of this, we keep that according to the product rule. The derivative of this is going to be 2r, because you bring the 2 down and then subtract a 1, you have that, and then you keep this as it is, plus we keep this one as it is, and we take the derivative of that, And of course, if we were having x raised to 1 over 2, the derivative of this, we know that it is supposed to be 1 over 2 times x raised to 1 over 2 minus 1. And of course, 1 over 2 minus 1 is going to be minus 1 over 2. But now we are not having any x, so we keep that thing that is actually sitting in the value of x, and then as it is, and then we keep this half that we're supposed, minus half that we're supposed to have, but now we take the derivative of the inside, multiply by it. The derivative of 100 is 0, and the derivative of minus 2r is the same as minus 2, because we bring this one down and then we get that. That's how we ended up getting that. We are using product rule, and then when we are dealing with this derivative of this, we end up using the chain rule. So we end up having 1 over 3 pi, and then inside here we'll end up having 2r, and then we end up having 100 minus r squared, and then we have 1 over 2, and then we have a plus here. And then the next thing that you want to realize here is that this 2 here will cancel out with that 2, and then we'll end up, instead of having a plus, I have that minus there and I have a plus, so we'll end up having a minus r, and then I have r times r squared. I will have r cube, and then I have this, but it's negative, so it's going to the denominator, and then it's going to be positive 100 minus r squared raised to 1 over 2. I think that is just it about this whole thing. And then let's simplify. 1 over 3 pi, and then inside here what we'll end up having, we'll have something very much interesting. We'll end up having 2r, and then we're gonna have this, which is the same as the square root of 100 minus r squared, and then I have minus, I will have r cube divided by 100 minus r squared, and then I have a square root. And then of course this one does not have a denominator, this one have a denominator. This is the same as times a 1, and this one here we're gonna use 100 minus r squared divided by 100 minus r squared, so that I have the common denominator and common denominator this side. The next thing that you wanted to do, you will end up having 1 over 3 pi, and then inside here you will end up having 2r times this one times that is going to be just 100 minus r squared. Remember that this times that will end up having this whole thing squared, so the square will remove this, so we'll end up having that, and then minus r cube all divided by the square root of 100 minus r squared. So that's how we end up having this whole thing. So we can even simplify further if we want to. We have 1 over 3, and then we have pi, and then inside we'll end up having this one is going to be 200r, and then minus 2r cube minus r cube all over the square root of 100 minus r squared. And then if you look carefully into this, you will end up having 1 over 3 pi, and then inside you will end up having 200r minus, and then we have 1 and 2, so here you will end up having a 3r cube all over a square root of 100 minus r squared. And then I think for now we can actually end up end up stopping there, that we are having v prime of r is actually this derivative. The next step that you want to find here, you want to find the values of x whereby this is equal to 0. When is this gonna be equal to 0? So if you want this to be equal to 0, you want, this one is a constant, it cannot be equal to 0. So, but I can just, for heaven's sake, to say 1 over 3 pi, and then I have this nice thing here, 200r minus 3r cube, and then all over the square root of 100 minus r squared must be equal to 0. And this one cannot be equal to 0, or I can divide on both sides. which means that this is the only part that can actually be equal to 0. For this thing to be equal to 0, the denominator cannot be equal to 0, because once the denominator is equal to 0, this whole thing is going to be undefined. So this thing is only going to be equal to 0 if the numerator is equal to 0, which means 2r minus 3r cubed is equal to 0. In other words, I'm going to take my r, I'm gonna take my r out, so I will have r, and then I will be left with 200 minus r squared is equal to 0. In other words, if r is equal to 0, or 200 minus r squared is equal to 0, which means that I have 200 is equal to r squared, and then I take the root on both sides, so we'll end up having r is equal to plus or minus the square root of 200. But if you look into this, the radius is always positive, so when r is equal to the square root of 200, so that is actually what we will actually end up having. There's something that I made a mistake of here. This, we're supposed to end up with a 3 here. We're supposed to end up with a 3. When I'm taking only the r, this is going to be 200. There must be a 3 somewhere there. And then, of course, we're supposed to end up with a 3 there. And, of course, we end up having a 3 there. And, of course, the next step here was just supposed to be 200 over 3 is equal to r squared. And therefore, r is going to be plus or minus the square root of 200 over a 3. But r is positive, so we'll end up having the positive square root, because the radius can never be negative. So we are having this r, and we're also having this r here. Which one is actually going to minimize? We don't know. We are about to find out. The second thing that you want to find the values. Find the values of x, making the first derivative of the volume with respect to r undefined. So this one is only going to happen when the denominator is equal to 0. Because we're having a fraction here, this is actually our v prime of r, and also this thing is only going to happen if the denominator is equal to 0, and this is the part that can actually cause us that, which means that this is only going to happen if the square root of 100 minus r squared is equal to a 0. If I square on both sides, if I have 100 minus r squared is equal to 0 squared, so I'm going to square both sides, then I will end up having that. And also, if 100 is just equal to r squared, or if r is equal to plus or minus the square root of 100, and you know that the square root, r can always only be positive, it cannot be negative. So if r is a positive value, in other words, if r is just equal to a 10, so we are having critical values here. R is equal to 0, r is equal to square root of 200 over 3, and r is equal to a 10. So these are the critical values that we are actually having here. So we have the volume, when this is equal to 0, want to evaluate that. The volume when r is equal to the square root of 200 over 3, and we also want to check the volume when r is equal to a 10. So these are the things that we wanted to end up checking. What was the volume? So this was the formula for the volume here. What is this? So this was the formula for the volume. So the volume is 1 over 3, and then multiply by a pi, and then we have r squared. We have r squared, and then we have a square root, and then we have a 10, so we have 100 inside 100, and then minus, and then we have our r, and then it is squared. That is actually the volume that we actually end up having. Let's look now when r is equal to 0. So if we are having a 0 here and a 0 there, what are we going to get? We'll end up getting a 0. And then if let's say now we are having a 10, I'm just gonna place a 10 there and also place a 10 there. What are we going to get? We are also going to get a 10, I mean a 0 there. We'll end up getting a 0 if we are having a 10. And if we are actually not having any of those things, we are actually having a square root of 200. We have a 200, and then we divide it by 3, and then we go all the way and we come here. We have a square root of 200, and then we divide by a 3. What are we getting? We end up getting a 400. A 403.07. The units that were given here centimeters, so we'll end up having centimeter cube, and centimeter cube. And then if you look into this one here, we wanted to maximize the volume, so the maximum, not just the maximum, so the absolute maximum is given by the absolute maximum volume is given by 403.07 centimeter cube with, what is the value of r? Value of r is just the square root of 200 over 3, which is approximately equal to, so we have the square root of 200, not 1000, divided by 3. This one is approximately 80.16, I can even say 5 centimeters. And then the height, remember what was our height here? The height was given in this formula here. So we're having our height as r squared minus this, and our r was 10, so it's 100 minus r squared. So we know that this one was given as r squared minus small r squared, which is the same as a 10 squared minus r squared. And of course this one here is actually the square root of 200 over 3, and then you square it up. Therefore our h is going to be 100 minus that. I want to find the actual value, so I'm going to have here, I will have a 10, and then I'm going to square it up, and then I'm going to say minus the square root, and then I'm going to have, no, I don't need that. I will end up having this thing here. So we end up having h as 10 root 3 over 3, or simply approximation of 5.77 centimeters. I think that's it, because the square will remove the root. That is why I don't have a root there. That is what we are having in question number 9. So those are the dimensions we're looking for. What is the radius of the cone that maximizes? Actually, they did not want this one, they only wanted that. So it's one of the things that actually we actually wanted, excuse me. So that's how we ended up solving for the radius, which is 8.165 or 8.17. So we are actually having that. And then the next thing, which is the last one, is question number 10. What is question number 10? Question number 10 is saying a rectangular beam is to be cut from a cylindrical log of radius 10 centimeters. So the radius is given. What dimensions of the rectangle will maximize the area of its cross section? So let me first try and draw some things here. Maybe we'll end up getting what is happening. We are at number 10. So number 10 is saying that we are having a cylindrical log a cylindrical log which is of this type here. So we are having a cylindrical log of this type. This is not good looking, but I'm trying, guys. Really trying. So we have this thing here, and of course if let's say this was cut from A3, it will be having those rings, nice rings there, and of course we'll be having something like that. You can see that it is a cylindrical log. So we are having this thing here, and they are telling us that what is actually happening here. Where's this question now? I don't want to end up doing my own things. A rectangular beam is to be cut from the cylindrical log of radius 10. What dimensions of the rectangle will maximize the area of its cross section section? So dimensions of the rectangle. So from this point, let's say from this point to let's say that point there, this is our radius. So this radius here is r, and it is equal to 10 centimeters. Let me just double check. It is equal to we have 10 centimeters. So we wanted to create a rectangular beam from this. In other words, we wanted to cut from this position to that position, cut from this position to let's say somewhere there, and cut from this position to that position. And of course we have this side here. I'm trying, of course this is not drawn to scale, so we want to cut, but this is also where we will end up cutting. And then we cut from that side, we cut from that side, and we end up there. And then we cut from this side, we end up there, and then we get something of this type. And then we cut from that side, we end up there, and we cut from this side, we end up there, and of course we get something of this type here. So we'll end up having a nice beam. This is going to be a nice rectangular beam. So we have a nice rectangular beam. That is what we are actually getting here. We are cutting it from here. But if you look into this, moving, let's say from this point here to that point, you will notice that it is the same point from that point. So I know that this one is supposed to be 10 centimeters, and from moving from this point to that point, that's supposed to be the same thing. And from moving to that point supposed to be the same thing. From moving to that point, we're supposed to be having 10s throughout. We'll end up having, I think it's supposed to be 10, and it's supposed to be 10 throughout. That is what is supposed to happen. I'm just trying to analyze here. We have this 10 centimeters somewhere. So let's look again at the problem. Let me go and bring this thing up. This question is saying a rectangular beam is to be cut from a cylindrical log of radius. What dimensions of the rectangle will maximize the area of the cross section? That's what I wanted to find out, the cross section. So if you look at the cross section, we are talking only about, let me move this a little bit. I'm going to make it like this here, and then I'm going to move this. So the cross section is this side. So we're talking about this nice side. So this is the cross section. So we wanted to maximize the area of this side. We have talked about this, that we wanted to maximize this area here like this. This is not hard, guys. It's just the matter of analyzing this. And one thing that you already know, you know that this side is going to be 10 plus 10. So the diagonal is just 20, or this diagonal is just 20. So want to maximize this area here. So what we do, we're gonna call this side the height, and then we're gonna call this side, let's say maybe that's the length or the width, or we can just use x and y. I think they are more familiar. So we're gonna use y for height and x for the width. Now what is important about this nice thing here? From this information here, you know that a rectangle have 90 degrees here. So this angle is 90, this one is 90, this one is 90, this one is 90, which means that we can actually cut out and say we are actually having a triangle here, whereby of course this is a triangle, this is 90 degrees, this is y, this is x, and this one is 20. And from this triangle here, you can see that using Pythagoras theorem, y squared plus x squared is just equal to 20 squared, because this side here is the hypotenuse. In other words, it is a side opposite to the 90 degrees. And of course here, if you are solving for y, you will have y squared is equal to 20 squared. That's supposed to be just a 400. Let me just confirm. So we are supposed to end up having a 400 minus x squared, or our y is going to be plus or minus the square root of 400 minus x squared. But because y is the height of something, so the length is always positive, so we'll end up having our y as that. Now that we are having this, we know that we want to end up realizing something, that we are having this here, and we want to maximize, let me go back, we wanted to actually maximize the area of the cross section. How do you find the area of the cross section? The area is just equal to this side times that side, so you have y times x. And if we want the area in terms of x, we can just eliminate y and say that we are having the square root of 400 minus x squared, and then we're multiplying this whole thing by an x. So this is actually going to be our function here. The next thing that we need to do, of course, you can look at the restrictions. We are not really given any much of the restrictions here, but we know for a fact that because x is we know that our x must be greater than 0, and also our y must be greater than 0 because they are height. And also another restriction, we can get it inside here by saying that we wanted to make sure that our y squared, our x squared is actually less than 400, and then we can actually end up solving this thing here, which is you will end up having you'll end up having to solve this and say that you end up having x, the critical values is going to be x is equal to plus or minus 20, and then after that you can see that the part that is going to be negative, because this one is going to be positive, anything that is out there, we will say now our x is always going to be in between 20. So we have x less than or equal to a 20. So that is the x that we can actually end up having. We wanted to end up having this contained, because once this becomes too big or too small, this is not going to be defined. So we can see that we are actually end up having this, and not only that, combining this with that, we'll end up saying that we are having 0 is less than x and x is less than a 20. So you are using this one because you want this to be defined. So you want this inside here to be defined. So you want what is inside the root to be bigger than or equal to 0. This can only happen for this when this is equal to this or equal to that. But now we know that our x must be bigger than 0 because x is the side. In order for us to end up having a rectangle, one side must be greater than 0. That is why we end up not putting that. And also next, we know that this must actually be bigger than 0, so we start there. And then secondly, we don't want our area to be 0, because once it is 0, either this side is equal to 0 or that side is equal to 0. That is why we don't want equality. That's why we end up having this, and we end up ending with that. So the restrictions of this that. But because 0 is not included and 20 is not included, it is enough to only check the turning point of these functions only. We don't have to check this because they are not included. But if they were included, you have to check them, which one is going to give you a max and which one is going to give you the mean. The next thing, remember that we have our a as a function of x is equal to, we have a 400 minus x squared, and then this whole thing multiplied by x, which is just the same as we have a 400 minus x squared all raised to 1 over 2 times an x. We find the derivative with respect to x. The derivative of this is only going to be simple. You keep that as it is. Or let's keep this first. You have the 400 minus x squared raised to 1 over 2. And then we take the derivative of that, which is just a 1. And then plus, we keep that, so we'll have x, and then take the derivative of that. If this was x, we're supposed to end up with 1 over 2, and then have an x inside, and then end up having a minus 1 over 2, because when you're separating there, we'll have a minus 1 over 2, times the derivative of the inside, which was supposed to be a 1. But now we don't have an x here. We have a 400 minus x squared. So we end up having to take the derivative of the inside, which is just going to be a minus 2x. So that's how you end up getting this. This one is going to cancel with that. And of course, we'll end up having a 400 minus x squared. This thing here is saying that you are having a square root. And then we have this minus and a plus, so we'll end up having a minus, and then we'll have x squared, because x times x is x squared. And then we multiply, we have to divide by this because the exponent is negative. So we'll end up having 400 minus x squared, and then we end up having this, the positive exponent, which is 1 over 2. But 1 over 2, we know very well that it is just the same as the square root. So that's what we are getting here. This, and then this one is that, and this one goes into denominator. And of course, this is the same as the square root of 400 minus x squared times 1, and 1 is just the same as the square root of 400 minus x squared divided by the square root of 400 minus x squared, and then minus x squared all over the square root of 400 minus x squared. And then moving from this, you can actually see that this and that is the same. So this is the same as just having this squared, and the squared will remove this. Let me write it so that I'm not too fast. I will have a 400 minus x squared all over a 400 minus x squared, and then we have a minus x squared all over a 400 minus x squared inside a root. I have this and that on both sides, so I can place it, take 1 and put it in the denominator. That's why I was changing a 1 like this, because I wanted to have a common denominator. And then this square root squared, you will end up having a 400 minus x squared, and then here we'll have a minus x squared, and then you're having a nice thing here which is saying x squared and x squared, so we'll end up having 400 minus 2x squared all over the square root of 400 minus x squared. The next thing that you wanted to do, remember that this one is actually the first derivative with respect to x of the area. We're just simplifying here. The next step is you want to find the values of x that are making this equal to 0. So you set it equal to 0 and solve for x. This thing here is only going to be equal to 0 if the numerator is equal to 0. In other words, if we have 400 minus 2x squared is equal to 0, because if this one is equal to 0, this whole thing is going to be undefined. Then let's solve. So we'll end up having 400 is equal to 2x squared, and then I divide on both sides by a 2. So this side will end up having 200 is equal to x squared, and also x is going to be plus or minus the square root of 200. But my x is actually what? It is the length of the rectangle, so we cannot have a negative length, so this x is going to be a positive. And then once you are having this x here, the next thing that we wanted to find out here, we want to find, find the values of x making a prime of x undefined. So this is only going to be undefined. This is only going to happen if the denominator is equal to 0. Denominator is equal to a 0. In other words, if I am having the square root of 400 minus x squared is equal to 0, because that's the denominator of this. And if this is happening, I am going to end up squaring on both sides, so I'll end up having a 400 minus x squared is equal to 0. And then I can take this to the other side, so I'll end up having a 400 is equal to x squared. And then I take the square root on both sides, so I'll end up having x plus or minus the square root of 400. And of course, if you look into this, x is the length of the rectangle, so x is always going to be positive. In other words, our x is going to be a 20. So what is the square root of 400? Just to be sure, it is a 20. Now we have this critical value. We also have what are the other critical values? We have this critical value, and we also have the other critical values, which is this one here, square root of 200. What is the square root of 200? The square root of 200 is just the same as 10.2, which is approximately equal to 14.14, and also this one here, just a 20 something. The next thing that you need to do, you want to find what is the area of the square root of 200. And then the second thing is what will be the area when x is equal to 20. So we have a 20 there. So we have those two things. And what will be the area when x is equal to a 0? So bear in mind that this 0 that I'm actually checking here is this 0 in the interval. So if this was equality, you have to check it, but in this case you don't have to check it. And also this one here, because it is not included, you don't have to check it, but I am checking it so that you get used to checking it, so that you don't end up making mistake when you are supposed to check it. I want you to also realize that this 20 came twice. It came here when you're looking for the interval, and also it comes when you're checking the critical values. So I'm checking this 0 and this 20, and also I am checking this 200 and this 20. So I'm supposed to have 4, but unfortunately this one is also contained on the interval. That is what is important here. Like I said, this one here, when it's not included on the interval, you don't have to check it. I am just checking it because I want you to get used to checking these things. This one is the one that you actually need to check. And yeah, so what was the original function here? What was our area? So our area was this. So our area was we had, what am I doing now? So we had the square root, open square root, we had 400 minus squared, close, open. So that is actually this area. Let's go down and check these values here. So here, when we are having the square root of 200, what are we going to get here? The square root of 200, not 4, square root of 200. The answer we'll end up getting here is just a 200. So we're having a 200 here. Let me write it black, so we'll end up having 200 centimeter squared because it's area, so squared, and the volume is cube. We're using centimeters, I hope. We're having that. And then when we're using a 20, we have a 20, and then here we also have a 20. So when we're having a 20 here, we'll end up having a 0 centimeter squared, and when we're using a 0, what will end up happening? So you will also end up having a 0. So you were going to check, even if you are checking it, the question here was saying maximize. So you can just say, because this is the largest field, so the absolute maximum area is given by 200 centimeter squared with dimensions. So we have the dimensions. Of course, our dimensions, our x is equal to, you look at this value which is giving us a max, is going to be the square root of 200, which is approximately equal to the square root of 200, which is just approximately, okay, for the purpose of the max, this is expected that you place it as 10 square root 2, which is just approximately equal to 14.14 centimeters. And of course, our height, which is y, we know that. How did we get our y? Where was y here? We had our y here. Where was y? Y was just the square root of 400 minus x squared. So y was square root. So it was square root 400 minus x squared, which is just square root of 200 squared. This is going to be the same as the square root of 400 minus, I have a square root here, square root, and that this will undo that, so I'll have a 200 inside. So I'll end up having the square root of 200 here, because 400 minus 200 is just 200, is the same as that. So I'm having the square root of 200, which is just the same as if you look into this, you know that this is 2 times 100, which is the same as the square root 2 times the square root of 100, which is the same as the square root of 100 is a 10, and then the square root of 2 is just the square root of 2, which is also approximately 14.14 centimeters. So you can end, let's say, at that particular point to say that you are getting your values there. So those are some of the things that we actually need to have to solve these questions. We wanted to find these dimensions, rectangle, what dimension? So these are the dimensions. X is equal to 14 point something, and also y is 14 point something. Now I want us to look at part C. Our part C is actually some of the realistic problems that I want us to actually look at. These are some of the problems whereby you actually need to think through before doing anything. The previous problems were very straightforward and easy. These ones will require us to actually think outside the box. So I want us to do these problems one by one.